Yes, hello everyone. So let's start today's session. So today we will study the packing efficiency of simple cubic, BCC and FCC. So first of all, what is packing efficiency? So let's have a look at it. One second. Okay, so packing efficiency, it is the fraction of the space occupied by the spheres. Okay, so packing efficiency. Packing efficiency is the fraction of the space occupied by the spheres in a crystal. So a miniature version of the crystal is a unit cell. So we take into account a unit cell. Means if we define it, it is the fraction of the space occupied by the spheres in a crystal, or we can say, because we are dealing with unit cells, so in a unit cell. Okay, because what fraction of the space is occupied with the spheres in a unit cell, same is extended to the crystal as a whole, because unit cell is reflection of the crystal. So we take into account a unit cell, and that unit cell, what fraction of the space is occupied by the sphere in a unit cell, same fraction is occupied by the sphere, same fraction of the space is occupied by the spheres in a crystal, right? So its formula is, or we can define percentage of the space occupied by the spheres in a unit cell. So packing efficiency, it is equal to volume of volume occupied by spheres in a unit cell divided by volume of volume of unit cell. One second. Divided by volume of unit cell. Okay. Yes, beta. Is it clear up to this? That volume occupied by the spheres in a unit cell divided by volume of unit cell. Now you know if Z is number of atoms or number of spheres per unit cell, and you know if R is radius of sphere, then what is the volume of sphere? Yes, beta. Can you tell me? If Z is number of spheres per unit cell and R is the radius of a sphere, then what is the volume of each sphere? What is the volume of sphere? So volume of sphere is, yes beta. Yes, tell me. Fast. It is very good. It is 4 by 3 pi r cube. Good. So 4 by 3 pi r cube is volume of sphere, and if A is edge length of cube, because we are considering cubic system, we are calculating packing efficiency for simple cubic, body centered cubic and face centered cubic. So if A is edge length, what is the volume of the cube? That is the unit cell. So what is the volume of unit cell? Volume of cubic unit cell is equal to A cube, right? So it is, yes. Good afternoon. Right. So now packing efficiency that is equal to, and it should be multiplied by 100 as well, right? To calculate percentage of the space occupied. Okay. So, to calculate volume occupied by the spheres, it equal to number of spheres per unit cell into volume of each sphere divided by volume of unit cell. So it is equal to into 100, right? Sorry, every time I forget to write this. Now packing efficiency is equal to, now I write the short form, that is PE. So number of sphere per unit cell, Z. Z is number of spheres per unit cell, and volume of each sphere 4 by 3 pi r cube divided by volume of unit cell, and that unit cell is cubic, so it is a cube. So in short, it comes out to be 4 by 3 pi into Z into r upon a cube into 100. So this is packing efficiency. So packing efficiency is 4 by 3 pi Z r upon a cube into 100. Means to calculate packing efficiency for simple cubic, body centered cubic or face centered cubic, first we should know number of spheres per unit cell, and then relation between R and A. That's what we need, right? So let's calculate packing efficiency one by one. First, let's calculate for simple cubic. Now in simple cubic unit cell, spheres are at the corners only. Spheres occupy spheres occupy each corner. Okay, and the spheres on the corners, they are in touch with each other along the edges. Spheres are in touch with each other along the edges. This is what we need. So first, sphere occupy each corner. From that, we calculate Z. So in simple cubic unit cell, spheres are occupying each corner. And each corner is shared by how many unit cells? Yes, beta. Each corner is shared by how many unit cells? Each corner is in touch with how many unit cells? Yes, tell me. Each sphere is in touch with how many unit cells? So keep in mind, each sphere on the corner is in contact with 8 spheres. How many spheres? 8 spheres, okay? So that means in this case, Z is equal to number of corner atoms into 1 by 8. And how many corners are occupied? You know, cube has 8 corners. So 8 by 8 means number of spheres per unit cell in simple cubic is 1. Okay. Now, second part. Spheres are, yes, tell me. Spheres are touching each other along the edges. So take it as A and this one as B. This is H. So they are, we are showing only one edge. This is the edge. So AB is edge length, and you know we have written edge length of the cube is A. Okay, and in terms of R is the radius of the sphere. So R, and this is also R, means equal to 2R. So in terms of edge length, edge is A, and in terms of radius of sphere, edge length is equal to 2R. That means relation become A equal to 2R. And what we need? We need relation between R and A. So R and A, so R upon A comes out to be 2. So this is the relation. So just put the values in packing efficiency formula. It is 4 by 3 pi into Z into R upon A cube into 100. That we have already calculated. So packing efficiency for simple cubic, that is 4 by 3 pi into Z into R upon A cube into 100. So just write the value. What is Z for simple cubic? It is 1. And what is the relation between R upon A? It is 2. So R upon A, that is equal to 2. Somewhere it gets wrong. It is 4 by 3 pi R upon A cube into 100. So A equal to 2R and R upon A equal to 1 by 2. Sorry, here we are getting wrong. R upon A, that is equal to 1 by 2. So this becomes 1 by 2 cube. So equal to 4 by 3 into pi into 1 by 8 into 100. So 4 to the 8. That means it becomes pi by 6 into 100. So if we say packing fraction, so packing fraction for simple cubic, it is pi by 6, or we can write it as 0.524. Okay, and packing efficiency, that is 0.524 into 100. So it comes out to be 52.4%. So that's it. So you should keep in mind in terms of pi as well, because that is asked in competitive exams. Okay, what is packing efficiency in terms of pi? So in terms of pi, it is pi by 6, that is packing fraction, or in number it is 0.524, and packing efficiency is 52.4%. So what is the percentage of the space unoccupied? This is the percentage of space occupied. So percentage of the space unoccupied. in simple cubic or primitive unit cell. So it is equal to 100 minus 52.4. So it comes out to be, yes beta, it is 47.6. So this is the percentage of the space unoccupied in simple cubic unit cell, 47.6%. Yes beta. Any doubt up to this? Any doubt beta? Okay. If you have any doubt, you can ask. Okay. So let's go to the next, that is packing efficiency of FCC. Packing efficiency of FCC unit cell. So in FCC, spheres are at the corners as well as face centers. In FCC, spheres are occupying corners as well as center of each face centers. Okay, so you know in addition to the atoms at the corners, there are, in addition to the spheres at the corners, there are spheres on the center of each face. So you know what is Z now? Yes beta, what is Z? Z is, corner atoms. Each corner atom is shared by 8 unit cells, and each face centered atom is shared by 2 unit cells. So it comes out to be 8 by 8 plus, how many faces are there? 6. So 6 by 2, that is 1 plus 3 means 4. So Z for FCC is 4. Z is 4. Okay. Now after getting this, now next part is relation between R and A. Relation between R and A. So let's find out the relation between R and A. In simple cubic, in FCC, spheres are touching along the face diagonal. Spheres are touching along the face diagonal. So A, B, and C. AB equal to A. BC is also equal to A because A is the edge length of the cube that we have already wrote. Okay. So now AC, this is right angle triangle actually. ABC is right angle triangle. So we apply Pythagoras theorem. AC equal to under root AB square plus BC square, that is equal to A square plus A square, that is equal to 2a square means AC is under root 2a. AC equal to under root 2a, and spheres are at the corners as well as at the center of the face. So in this way they are touching each other. So AC is equal to, in terms of R, AC equal to, this is R. What is this? 2R, this is R. In total it is 4R. That means under root 2A equal to 4R. So what is the relation between R and A? Yes, that is also very important. In first case, what is the relation between R and A? This is the relation, A equal to 2R. And distance between the nearest neighbors equal to 2R. That is also important. Distance between nearest neighbors, that is equal to 2R, and that is equal to A. That is also one part, and that second is relation between R and A. So A equal to 2R, or we can say R equal to A by 2. Okay, in simple cubic. Now in FCC, what is the relation between R and A? R equal to under 2 by 4A, or we can say it is equal to A by 2 root 2, or A equal to 2 root 2R. And distance between nearest neighbors, that is A by root 2. Distance between nearest neighbor, take it as D. So that is equal to 2R, and that is A by root 2. Okay, so R upon A, that ratio is equal to under 2 by 4, or we can write 1 by 2 root 2. Right? That's it. So just put the values. So packing efficiency in FCC, so it is 4 by 3 pi into Z into R upon A cube into 100. And what is Z for FCC? Z for FCC is 4. And what is the relation between R and A? One by 2 root 2 cube into 100. So 16 pi by 3 into 1 by 16 root 2 into 100. 16 cancel. So it is 5 by pi by 3 root 2 into 100. Just multiply by under root 2 in the numerator as well as denominator. So it comes out to be under root 2 pi by 6 into 100. So packing fraction for FCC is under 2 pi by 6 and it is 0.74. So packing efficiency, that is 0.74 into 100 and it is 74%. It is 74%. Rahul, thank you, beta. So in addition to that, now what is the fraction of the space unoccupied? Yes, beta. Percentage of the space unoccupied. What is the fraction of the space unoccupied? Yes, fraction of the space unoccupied. So fraction of space in FCC, that is equal to 100 minus 74 means 26%. It is 26%. Yes, beta, right? So fraction of the space unoccupied is 26%. So now last one, that is body centered cubic. So in body centered cubic, spheres are occupying corners as well as body center. Means in addition to the atoms at the corner, there is one atom at the center of each, or center of the body, sorry, center of the cube. There is only one center, you know. So corners and one atom is at the body center. Okay. So tell me now, what is Z? So Z comes out to be, you know, corner atoms divided by 8 plus one atom at the center, which is not shared by any other unit cell. So it is 8 by 8 plus 1, that is 2. So number of spheres per unit cell in BCC, that is 2. So this is a Z. Now what we will calculate the relation between R and A. Now in BCC, see, in FCC, spheres are touching along the face diagonal. I will write here also. In FCC, spheres are touching along the face diagonal. On the same line in BCC, okay, but the question is, in BCC or FCC, we have to know the number of spheres per unit cell, number of particles per unit cell or its packing efficiency, that we should know, or at the same time we know how many atoms per unit cell are there, what is the relation between R and A. That is what is expected to find out that whether this is BCC or FCC. Okay, okay, you should know Z and relation between R and A, that is expected. Okay, so now come to next, that is BCC. In BCC, spheres are touching along the body diagonal. In BCC, spheres are touching along the body diagonal. Okay, so as spheres are touching along the body diagonal, say this is body diagonal A, C and D, and ACD is right angle triangle. So you know AC we have calculated in terms of A, that is under root 2A, and CD is A. So in right angle triangle ACD, AD, that is equal to AC square plus CD square, and AC we have calculated in FCC. So it is under root 2A square plus A square. So it is 3A square. Under root 2A square means 2A square plus A square. So 3A square means under root 3A. So AD is equal to under root 2A